Hey everyone, welcome back to my daily coding series. This is episode 95. So today, I had a lot of fun yesterday with the hard graph problem, so I'm going to try another one. This one is called word ladder. So I've looked at it briefly, but this is the first time I'm going to think about solving it. This is not a tutorial, but a live problem solving video. So, alright, let's look. So we have word ladder, which is hard. You're given two words, begin word and end word, and also a list of words. All words are the same length, consisting of lowercase English letters, and are all distinct. Your goal is to transform begin word into end word by following the rules. You may transform begin word to any word within word list, provided exactly one position the words have a different character and the rest of the positions have the same characters. You may repeat the previous step with the new word that you obtain, and you may do this as many times as needed. Return the minimum number of words within the transformation sequence needed to obtain the end word, or 0 if it's not possible. Okay, so my understanding is we have this word, and we can transform it into any one of these, and then once we have any one of those, we can transform it into any other one in the word list, and eventually we want to get to the end word. Does the end word have to be in the word list? I see here that it is. Okay, it does have to be in there. Because here it says SAG is not in the word list, so it's impossible. So the end word must be in the word list. And let's look at the edge cases here. So we have... okay, so they're all the same length of characters, so they have to be at least one character, and then the word list length has to be at least one. Alright, so it can't be empty. They all have to be the same length. Excuse me, they have to be the same length and distinct, and it's all but one. They're all distinct. Your goal is to transform. Okay. So the way I'm thinking about doing this is, first, of course, we want to build the graph. And the graph, what we're going to do is, or what I think we could do, is take cat and then compare it against every one of these and see which are its valid transformations. And then make cat point to those. Then we'll take bat and we'll go through all of them and see which are its valid transformations. And then take bag and see which its valid transformations are. And then sag, right? So that's going to be sort of like an n squared behavior. So for every word, so it's going to be the number of words times the number of words times the word length. And the reason it's times the word length is because that's how we determine if it's a valid transformation, is we're going to have to go through every character until we find two different characters, then we know it's not valid, or until we get to the end of the word, which it would be valid. I'm just going to write that down. To determine if edge exists, iterate through word and find two mismatches or get to end of word. Okay, so once we have the graph, we want to find the shortest path. Find shortest path. yeah, we want to find the shortest path from begin word to end word. And how will we find the shortest path? I mean, what we could do is maybe give each, like we can just have a count and kind of do like a Dijkstra sort of thing where the edges will be of length 1. Like the edge weights. Yeah, so I think we'll just have like, edge weights of 1 or something. We don't have to explicitly put that down, but maybe we could have with every word we could say, okay, so like bat, the shortest path so far is infinity, bag is infinity, right? So we'll do this, and then once we find this, we can compare it against the time it's taken us to currently get there, and then if this is smaller than our current path, then we can just skip it because that means we've already found a shorter path. And basically whenever we add back into the queue or the stack, however we want to do it, we just add like the current time plus 1 or the current number of transformations. So this is my approach. And then we will return like the dictionary of end word, and that'll be the min number of edits. Okay. So the hardest part is probably building the graph, I guess. And then, well, I'd say these are both pretty tricky. All right, so let's so also too, something that's easy to do, I think, is you can just do a linear check to see if the end word is in the word list. But it's possible that it could be in there, but it's still not possible. Like, for instance, so I was going to do something like if end word not in word list, then return 0, which is the no sequence exists. But this isn't the only case that it could be not possible. So for instance, if you consider the first example, if we have the begin word is cat, the end word is sag, and then in our word list, let's say we do have just bat and sag. So sag's in the word list, but it's still not possible because once you get to bat, you can't go to sag. So I'm going to hold off on this until the end, and we'll probably just check if, if sag equals infinity. So we could call it like, if the minimum distance of end word equals infinity, then return 0. Otherwise, we could return the minimum distance of the end word. All right. Yeah, so building the graph, I want to have a function that says like check valid pair, and what that means is check if it's transformable, or check if it's like how would you say it, transform. I'll just call it check transformable. So this will take in word 1, which is a string, and word 2, which is a string, and this will return a Boolean. Okay, so now they have to be the same length. So I'm thinking what I'll do is have a while loop and they're going to be the same length. And then we'll say if word 1 of I does not equal word 2 of I, then num errors plus equals 1. If num errors greater than or equal to 2, then return false. And then return so I'm thinking something like this. Yeah, this is probably the best way to do it. Yeah, so I'm thinking something like this, and the reason I'm doing this part and not just true, it's fine to do true here, but we do want exactly one mismatch. So I'm just going to return that there. So let me test this. So results equals let's try apple and that. So that says true. What if I were to change this to an F? That should be false now, right? False. And if I put them as the same word, then it should be false as well. All right. So that's good. All right. So now what I want to do is I want to iterate through like this. I plus 1. I want to iterate through like this and create our graph. So our graph will be a dictionary, and then we're going to make, all right, so if, and instead of check, let's say is transformable. So if word list of I and word list of J are transformable, and we also have to do this with the beginning word too, then so if they're transformable, then we want to add so graph of word list of I. Yeah, I'm just going to say word 1, word 2. Okay, so if word 1 not in graph, then word 1 graph of word 1 equals empty list. And graph of, this is a one directional graph. What if there's a cycle? Which there should be. Because bat points to yeah, because right now I'm doing bat. Maybe it shouldn't be a one directional graph. Well, it's not. Well, it's not really a one-directional graph actually, because every transformation is two-way applicable. So if you're at bag, you could go to bat, and if you're at bat, you could go to bag. So I think it's actually a two-way graph. But I think cycles will just naturally get cut out because it will take longer to do them, so they won't get added to the queue. All right, so we'll make the two-way connection. All right, so if it's transformable, we'll add the connection. Otherwise, we will not. And then, of course, we also want to say we also need we also want to check cat as well. So maybe I could just say for I in range length of word list, if is transformable, and then we'll say begin word and word list of I. Yeah, I wonder if I could make is there an elegant way to do this? Because there's some repeated code here. Because I'm thinking I want the pointers to save space so I don't like compare the same pair twice. But if I don't use pointers, it would be a lot easier to implement this. I think I'll just not worry about optimizing too early. So if it's transformable, then we'll and we definitely just want begin word. We know that's definitely going to be in there. So so we could say begin word, graph of begin word, dot append word list of I, and then if word list of I not in graph, then graph of word list of I dot append begin word. Okay, so here we're connecting the word list words to each other, and here connect begin word to word list words. All right, so that's our graph. So let me print the graph and see if it looks accurate at all. Oh, whoops, I did that wrong. Graph of word list of I equals empty list. All right, so cat goes to bat, bat goes to cat and bag. That looks right. Bag goes to bat, sag and dag. Sag goes to bag and dag. Dag goes to bag and sag. All right, so then where we would go is cat to bat, and then probably bat to bag, and bag to sag. That says 4. 1, 2, 3, 4. So it's the number of edges plus 1, really. Yeah, so we did transform, transform, transform. So the number of transformations plus 1 is the answer. Okay, so now we have the graph. It looks good. So now what we want to do, and then let me just see for the second case here what that looks like. So yeah, there's nowhere to get to sag. Okay, so now we're gonna do like we're gonna use the so now we're on so we built the graph. So now we're on step 2, which is find the shortest path from beginning to end. So yeah, so let's have a mins yeah, let's also so we'll initialize a mins dictionary here, which will have the words and then pointing to the shortest distance. So when we get here, we'll just say mins of word list of I equals float infinity. And yeah, so just because we're already looping through them. So yeah. So all of these get set to infinity. All right. So now we need to find the shortest path from beginning to endward. So I think the shortest path to the beginning is actually 0. Yeah. Okay, anyway. So I'll just do a breadth first search. Collections, import deck. Alright. So built the graph. I'll just move this up here, just so we remember the time complexity. Alright, so we'll initialize our queue is collections.deck. And what do we want in this queue? Probably begin. Alright, so I'm thinking what we want in the queue is a word and then like the current time or like the current transformations to get to that word in a tuple. So we'll have the word, which is begin word, and then we'll have 0. Like it's taken us 0 transformations. But maybe we could just start at 1 for the answers. I don't know. I'll just keep it at 0 and then probably add 1 to the end because that makes more sense to me. So while the queue, yeah, so let me do pseudocode first. So we're going to have, while our queue exists, we want to pop from that queue. We want to get the node and the number of transformations. And then for neighbor in node, yeah, so we want to check if mins of neighbor is less than, well, when do we want to add it? We want to add it if it's greater than, so I'm thinking if the number of transformations plus 1, I'm just going to call it t, because it could be t for time or transformations. But okay, so if t plus 1 is less than the graph, like the, no, not graph actually, the mins, so the minimum time found so far, then we want to q dot append left neighbor. And we want to append the neighbor with t plus 1. And we want to update mins of neighbor to equal t plus 1. If we found a shorter path before, we don't want to add it. Yeah. So all right. So is there anything I'm missing? And then at the end, we would just return mins of end word plus 1 if it's not infinity. Alright, so I guess I could walk through a solution with this, because I guess I could try, let me try just having this, and I'm not sure how it'll behave. I'm not sure how it will behave with cycles yet. So let's just see that. Mins of neighbor. Neighbor is C. Oh, for neighbor in graph of node. So we have to get the connections instead. I need to make this into a tuple because we are appending a tuple. That one works. This one, sag. Yeah, so it's not in there. So I think something else I'll do is probably end word with infinity. I mean, I could do a check early to make sure it's like in there or not. Okay. So yeah, I think because, so with a cycle, if you go to cat, if you're from cat, so cat has a timestamp of 0, and then you go to bat. Well, actually, none of these can go back to the start word, but let's say bat and bag, right? So let's say the minimum time you've had for bats is 1. Then you go to bag, and the minimum time is 2. When you check the neighbor of bats has a minimum time of 1. So when you get here, you're not going to add it back to the queue. And then let me fix this indentation because I did it inside of the comments. So let's just call it n times word length. And this is just a breadth first search, basically. This is. So, yeah, I think the trick of this part is just building the algorithm. Or, sorry, building the graph. I don't know if it's like, if my solution is slow or something. Let me see. So this one is called what? Word ladder. So let's see if it's on here. Word ladder. Yeah, because a lot of times what will happen, at least for me, is I do it on NeetCode and then it will like TLE on LeetCode. And let's just see. Yeah, so it looks like the same exact problem. Am I printing anything? Okay, I solved it, so that's nice. It looks like there's probably some faster way to do it, but okay, awesome. So that's great. That was a pretty good problem. I'm glad I was able to do it. Yeah, so that's every graph problem here. So there's advanced graph problems. I feel pretty confident with graph problems. I think I should probably focus my attention more on these dynamic programming questions, and then maybe start to research a little bit of bits, and then maybe some matrix problems and stuff like that. Yeah, I think I love doing the graph problems, but I think I'm pretty good with graphs, like good enough for interviews at least. So yeah, I'm gonna reapply my focus probably to like this area. But yeah, thank you for watching. That was 95, I think. So have a good day, and I'll be back tomorrow.